In this session, I'm going to explain about the secondary structure, mainly alpha helix. There are major three the secondary structures: alpha helix, beta pretty sheet, and loops. Alpha helix main chain has this kind of helical pattern. Different type of helix could be defined by using two parameters, P and N. P pitch indicate the distance per turn along the axis of column made by helical shape, and number represent unit number per turn. Residues in helix, alpha helix 1, 2, 3, 4, and start over 1, 2, 3, 4. In this slide, you can see the features of alpha helix. In A, just a helical shape made by main chain. So N in this case will be 3.6. In B, this is just a simplified drawing for alpha helix. Shows you the hydrogen bond formed and CO and NH. The striped lines represent hydrogen bond. In C, this is a ball and stick model for real alpha helix. Again, the hydrogen bond almost parallel to the axis. In D, you can see main chain plus side chains on the surface, pink color. In E, this is a top view. At the center, helically rotating main chain, and side chains just they protruding outward. This just summarizes the feature of alpha helix. It's right-handed. Phi torsion angle is minus 62 degree. Psi minus 41 degree for typical alpha helix, and 3.6 indicating 100 degree per residue. P is 5.4 angstrom, meaning 1.5 angstrom per residue. Hydrogen bond is made between CO of ith peptide, the peptide bond, and NH of I plus 4th peptide. Side chains are positioned outward, outside. I'm going to explain later about dipole moment. Proline is not good in making alpha helix because simply the phi angles is not matching with typical alpha helix. The average length of alpha helix consists of 10 residues, but it could be varied from 4 to 40. Some residues are very good in making alpha helix, such as A, E, L, and M. Some are very poor, such as P, G, Y, S. transmembrane domain also could form alpha helix. In this case, transmembrane domain could be alpha helix could be predicted from the residue sequences. More than 20 hydrophobic residues in a row. They are highly make transmembrane alpha helix. There are two reasons. First, alpha helix in global protein has usually less than 10 residue. Okay, and secondly, the hydrophobic core in bilayer is about 30 angstrom with this. To span this hydrophobic region, you need at least 20 amino acid with hydrophobic property in a row, because each residue spans just only 1.5 angstrom. To cover 30 angstrom, you need 20 at least. This shows the dipole moment. Single peptide bond, CO and H, they have a fractional charge shown in box, positive, negative. Again, positive, negative. So altogether, could behave as a single dipole moment, as shown at the center, yellow arrow. Again, positive and negative. In real alpha helix, dipole moment actually arranged in the same direction, so that the orientation just lead to the increase of dipole moment, and terminal has a strong positive charge and the negative charge in C terminal. In C, this is real the protein. Some helix has a strong binding to the phosphate, even though N terminal of this helix doesn't have any positive charge side chains near phosphate binding side the regions. This is a space filling model for the alpha helix. Outside you can see yellow colors for the side chains. At the center, colored regions are colorful regions are main chain. Main chains are actually highly compactly packed. There's no any empty space. Even though we can depict alpha helix by using helical field, you see at the bottom the residue sequences of one alpha helix in citrate synthase. Is mostly hydrophobic, green one, and polar, blue one. In center, you can see one alpha helix in alcohol dehydrogenase. So again, green is hydrophobic and blue is a polar, I'm sorry, and charged in red. But you cannot figure out easily the property of this alpha helix. But when you're looking at the helical field, this half has a hydrophobic surface, the other half polar or charged. So probability space may be buried into hydrophobic inside, and this one probably exposed to the surface or contact with the hydrophilic regions. In this case, all they are polar or charged. Okay. Now we could understand some baryon type of helix. There are several in this category. 310 helix first, meaning 3 residues per turn. 10 atoms are actually making the turns between two hydrogen bonds. In this case, hydrogen bond is made between ice and I plus 3, third. Pi helix instead making hydrogen bond between I and I plus fifths, so loosely packed. This one also has another name, 4.416 helix. According to this nomenclature, polypore 1, where purines, all purines present as cis configuration, they are making right-handed helix. Polypore 2, where all purines, they are making all trans. They are making left-handed helix. You can see the difference between alpha helix and C10 helix and pi helix in terms of the hydrogen bond made from here to here. That's going to be alpha helix. Here, that's going to be C10 helix. Here, pi helix. In next slide, you can see more clearly the actual helix. Alpha helix at the center, left side shows a 310 helix, much tightly packed, and pi helix on right side, loosely packed. These drawings just shows you the polypropylene 2. There is no any hydrogen bond in main chain. However, they could adopt the left-handed helix. Okay, polyglycine 2 also could make right-handed helix.